And again, this video is going to be simpler too. Maybe not as simple as the last video. You're going to have to remember your properties of logarithms. But if your 6.5 is solid, this isn't that bad. Again, it's really video 2 that's pretty tough. So we're going to do this video just like we did 6.6.1. That was exponential equations with a one-to-one property. Because yeah, exponential functions are one-to-one. They pass the horizontal line test. So if two exponentials are equal, then their insides are equal. Well, logarithms are also one-to-one. So if two logarithms are equal to each other, two logarithms equal each other, then we can use the one-to-one property on this as well. So that's what we're going to do here. As a note, you may have to combine logarithms. Oh, combining logarithms. We've been doing that. That was 6.5, combining logarithms. So here's one situation where combining logarithms makes sense. All right. So let's do some examples. Example 6. Solve. Part A. The natural log of 10 minus 3x equals the natural log of negative 4x. We can't take the natural log of a negative. But I'm not worried. Even though there's a negative here, it doesn't mean the inside's negative. Right? Negative 4x is not always negative. If x is negative, for example, then we get negative 4 times negative something else. So as long as x is negative 2, then we're taking the logarithm of something positive. So one logarithm equals another logarithm with the same base. So their insides have to be the same. Since same base, we can use the one-to-one property. Now we just solve this. Add 4x to both sides. That gives us 10 plus x equals 0. Subtract 10. X is negative 10. The one thing that is going to come into play sometimes is make sure that our answer is in the domain. It won't come up too often, but it'll come up sometimes. If x were a positive number, for example, there would be a problem. If x were 2, that wouldn't be a solution at all. So it's a very good idea to check your answer before you box. The natural log of 10 minus what becomes 10 plus 30. Is that equal to the natural log of 40? Yep. We're good to go. We're not taking the natural log of any negative numbers. Good idea to check your answer always. Let's do part B. Common log of x plus 3 minus the common log of x equals the common log of 74. So we don't have the same thing anymore. We don't have a single logarithm equal to another logarithm. We need the log of something equal to the log of something else, and we don't have that. There's too many logs. We have to combine. And the only way that we combine subtraction of logarithms is the quotient rule. This is the logarithm of x plus 3 over x equals the logarithm of 74, and now we can use the one-to-one property. So that's the only real thing here, is that sometimes you're going to have to combine. One-to-one property says two logarithms of the same base equaling each other. We've got that. So x plus 3 over x has to equal 74. Solve this equation. Anytime you have a variable in the denominator, you want to get rid of that. How do we get rid of a variable in the denominator? Multiply both sides by x. It's going to give us x plus 3 equals 74x. Subtract an x on both sides. You're going to get 73x equals 3. Or x is equal to 3 over 73. Is that right? This seems really weird. Did I make a mistake somewhere? I don't know. Let's check our answer. Let's go to our calculator. Check our answer. Is the common log of... Wait, what did I say our answer is? 3 over 73. It's common log of that plus 3 minus the common log of 3 over 73. Is this equal to the common log of 74? Oh, it is. So I thought it looked weird. Checked my answer. Checks out. The two sides of these equations equal each other. And it's in the domain. Good. Let's do some more. Log base 9 of 2 plus log base 9 n squared minus 7n equals the log base 9 of negative 45 plus n squared. I think my notes are real messy for this one. Let's see what happens. It's supposed to be n squared up here. And again, we need two logarithms equal to each other, so we need to combine. They all have the same base, which is good. Otherwise, we'd have to use the change of base formula. So this becomes log base 9, product rule, 2 times n squared minus 7n. Two logarithms the same base equal to each other, then their insides must be equal to each other. Let's distribute. And we've got a quadratic equation on our hands. Woohoo! Just like that second video. Quadratic equations, factor them. Quadratic formula, complete the square, all great methods. So with a lot of equations, we want the variable on one side and the numbers on the other. But remember, quadratic equations are usually easiest if we have everything on the same side. Kind of one of the exceptions because of the unique way that we solve quadratic equations. So let's move everything over. Let's subtract an n squared from both sides and add a 45 to both sides. That's going to give us 1n squared minus 14n plus 45 equals 0. And we're going to try to factor. We need two numbers that multiply to 45 to add to negative 14. So if they multiply into a positive number and they add to a negative number, they have to both be negative. So negative 1, negative 45, that adds to negative 46. That's no good. 2 doesn't work. 3, that adds to negative 18. 4 doesn't work. 5, there it is. This is n minus 5, n minus 9. And you can always check your answer every time you're factoring. FOIL this out, check our answer, see if we get it. N times n is n squared, that's good. Minus 9n, minus 5n, that's minus 14n, good. Plus 45, great, we factored correctly. So n is equal to 5 and 9. We just have to make sure that both of these are in the domain and we'll be good to go. Do not box your answer here. This is important. Make sure they're in the domain. Let's check our answers. All right, so check our answers. Let's plug in 5 and see what happens. Let's look at the left-hand side if we plug in 5. Left-hand side says log base 9 of 2 plus log base 9 of 5 squared minus 7 times 5. What? Uh-oh. Did I type this in right? Log base 9 of 2 plus log base 9 of n squared, n is 5, minus 7n, which is also 5. Yeah, it is not in the domain. Trash it. Throw it out. 5 is not a solution because it's not in the domain. We can't plug in 5. That gives us a logarithm of a negative number. Good thing we checked. Let's try plugging in 9. All right, so 9 equals something. Let's just make sure it equals the other side. The right-hand side was log base 9. Log base 9 of negative 45 plus n squared, and n is 9. Oh, good, they equal each other. And again, if you graphed both of these functions, right? If you graph these functions with n, I'm going to use x here. You graph both these functions, they only ever intersect. They don't intersect anywhere on the left. And they certainly don't intersect at 5, right? 5 is here. These graphs aren't even defined at 5. They do intersect when x is 9, just like we thought. All right. Let's do one more example. Oh, I don't know why this is red. Solve and graph both sides of the equations to verify. Three. Oh, wow, really? Yeah, that's what my notes say. I need to clean up my notes. 3 over log base 2 of 10 minus... No. Three over log base 2 of 10 minus the log of x minus 9 equals the log of 44. All right, I don't think I wrote this down right. Okay. So I could use the change of base formula to get everything in the same base here. But I think I just copied this problem down wrong. Let's do a different problem. Let's do the common log. Oh, we're back to red. Oh no. 4 minus 2x equals the common log of negative 4x. We have two logs equal to each other. They're equal to each other when their insides are equal to each other. Add 2x to both sides. That gives us that 4 equals negative 2x. Divide both sides by negative 2. Should get x equals negative 2. And we can check our answer by graphing it, since we're supposed to graph this anyway. All right. The common log of 4 minus 2x. Where does that equal the common log of negative 4x? The answer is at negative 2, just like we suspected. All right. And that's how we do it. Good luck, and let me know if you have any questions.